I'm really happy to introduce Dana Bartošová, who will speak about non-metrizable universal minimal flows.
Thank you, Anush, and thanks everyone for coming and for the organizers to organizing and inviting. Already there are invitations for conferences in September 2021 that are online, which is a little sad, but I hope that eventually we are going to get there. So I'm glad that Christian introduced notions, or he focused more on discrete and then locally compact groups and went from there. And this is what I have been looking at recently, and this is where the non-metrizability comes from, and it's sort of complementary to what I have been doing before, and I'm trying to connect that all. So what are flows? How can we see flows where our flows are going to be on compact Hausdorff spaces? And there are sort of two ways to look at flows, and one is to look at how a certain group acts on a, in our case, a compact Hausdorff space by continuous functions, and in case of group actions, by continuous homeomorphism. So we can think of that as a bunch of continuous maps where we have also joint continuity, or and in particular, when we are acting by integers, this is generated just by one continuous, by one homeomorphism. Or we can think of that as looking at the orbits, right? So I'm more looking at now fixing just a single point each time, and I'm looking at where that point moves around the space. And so this would sort of how an integer orbit would look like, just either an infinite line in both direction or some cycle. And then if we look at other groups, of course, it's every orbit is going to look either as the group itself or some sort of quotient of that. So I will be talking about integers and square of integers, right? So the orbit, the square of integers would look sort of like that, which is pretty much either a copy of the Cayley graph or some sort of squished Cayley graph by some equivalence relation. Okay, so for us, flows are going to be jointly continuous actions where we are acting by an arbitrary topological group, and the spaces are always going to be compact. And just to recall what an action is, well, if I act by a neutral element, that means that every point is just mapped to itself, and multiplication is the same as composition. So if I do two steps by G and by H, this is the same thing as by going, oh, I just wrote it in the opposite direction by GH in here. And as I said, if I fix an element of the group, then I get a homeomorphism of the space. So I will be thinking about the elements as homeomorphisms, and equivalently, group action or continuous action is a continuous homomorphism from G into the group of homeomorphisms on X with the compact open topology. And distinguishing between the systems and the spaces that we are acting on, right? So we have that this is the flow, and if I am looking just at the face space, this is this part. So ideally, we would like to understand the whole picture. That means that we want to understand what the face space is of a certain flow with certain properties, and how the group acts on it. And this is the case in some classes of groups, where basically the only way that we know how to find out what how some types of flows look like is by explicitly computing what the space is together with the action. And in some other cases, we are using less of the dynamical information, and we might know what the face space is, and we might not quite know what the action is. And this is the case when we are looking at discrete and locally compact groups up to date, as they have not been investigated from the point of view that I will be talking about as much. So as an example, I said that if I am looking at integer flows, because integers are just one generated, then every action, every flow is given by a single homeomorphism, and then every number n acts as an nth iterated either forward or backwards. So some notoriously known examples are, well, this is just going in a cycle on a finite group, or we can be looking at a continuous circle and looking at rotations by some number between 0 and 1. This is an interesting action, of course, and it might be relevant, but we are not there yet to, we haven't written up the proof yet. So in rotations, there's two types: the rational rotation, which is basically the first example, or irrational rotation, where the orbits end up being dense. Then the Bernoulli shift, this is an action on the Cantor space where we take the sequence of 0 ones and move it all to the left. And an action that we will be interested in today a lot is an action on the Chicstone compactification of integers. So this action is non-metrizable. So it has been studied mostly by set theorists and not as much by dynamicists. And because this is the space of all ultra filters on integers, and we will go into that example more later. So the type of flows that we are interested in are minimal flows, and one reason why we study minimal flows is that they're in a way building blocks of dynamical systems. It is not always the case. It's not that every flow can be decomposed into these minimal pieces, but we can understand a lot of the dynamics out of understanding the minimal flows. So minimality is here, and with respect to inclusion, so flow is minimal if it has no smaller flow inside. That means that there is no non-empty proper closed G-invariant subset, right? So we have the closedness here because we are only acting on compact spaces. So equivalently, we have that this means that every orbit is dense. And this is what Christian also said, that if I take a point and its orbit closure, this is a flow. So if this wasn't the case, that every orbit is dense, then we would have a subflow that is non-trivial and proper. That would be an orbit closure. Okay, and among the minimal flows, there is the largest one, or the most complicated one, which is called the universal minimal flow, that has every minimal flow as a quotient. So there is a continuous onto map that respects the actions or commutes with the actions onto every minimal flow. So there is different reasons to study that. Some are related to additive combinatorics in the case of integers, and you can think of that this is as far as you can get with complexity of minimal flows. And for instance, integers or any discrete group, even though it turns out to be non-metrizable, you can approximate that by metrizable ones, and that has been investigated quite a bit as well. And ideally, which there is a long way to go because there is still a lot unknown about what they are for different groups, and there is no unified way to really understand them yet, would be that if you know what it is, every minimal flow is a quotient. So you are trying to build a structure theory of all minimal flows. So examples, and the most trivial example would be a compact group. So of course the trivial group falls in there. So truly the most trivial we can get from this perspective, because then the universal minimal flow is just the multiplication. We are acting on the left, so that's why left multiplication. And then some non-trivial examples. First are infinite dimensional groups, in the sense that they are not locally compact. And an interesting example of all permutations where the universal minimal flow turns out to be the space of all linear orders. And this, together with Pestov's example, is one of the first ones in investigations of groups of automorphisms of structures. So Pestov's example is about group of bijections of rationals that preserve the rational order, where the universal minimal flow is trivial. So as I said, these are infinite dimensional groups, and we get that the universal minimal flows are metrizable, either the Cantor space or even trivial, and that cannot happen for groups that are locally compact. And as I said, there is not many of those that have been investigated. As for universal minimum flows, for integers, we know what the phase space is. So that's what I was pointing out, that here we do not really know what the action is. I can tell you what the space is, but I cannot tell you how one acts on that space. And this is because the techniques are from Boolean algebra theory and relies on that heavily, where you identify that it has to be this unique space, which it has to be a space that is extremely disconnected, and it is the stone space of the algebra of regular open sets of the Cantor space. But just see it that way. This is a huge space already, and this one is bigger modification of that. So this is the direction that we will be looking at, and there is a huge discrepancy. So before the break, I was giving a talk in Poland on distance, and I was really not well before. And when I gave the talk, I realized that people couldn't have had any idea why I was saying what I was saying. Motivation was poor, so I'll try to make up for it a little bit today. So what the all-over program would be to determine what spaces can be phase spaces of universal minimum flows. There are some general restrictions. If you have arbitrary topological group, there is a little bit that you can say. It cannot be just an arbitrary topological space. But of course, this is a big goal to really have a whole map of saying, if a group has such and such property, and that might be in terms of coarse geometry or some other ways, it's not clear what the criterions will be, then this is how the phase space would look like. I'm now focusing on locally compact groups in particular. And then interactions of algebraic operations. So we build groups out of simpler groups. And that especially appears in the structure theory of locally compact groups. So maybe there is some way to translate that into the universal minimum flows, and we could somehow have building blocks out of which we build more complicated examples, and then ideally, and this was structure theory of universal minimum flows, and consequently of minimal flows in general. Right. So, for instance, if I know that my flow is metrizable, right? So if I have in one, there has been some work done, especially for groups of automorphisms of first order structures that are countable. So think of the rationals here, or think of just the infinite set as we had in those examples there. So if the group is infinite dimensional, not locally compact, then this universal minimum flow can be metrizable, right? Here we had that it was just a singleton, and here linear orders are natural numbers, which is the same really as the Cantor space. So if it is metrizable, then there is not very many options for what the phase space is. So topologically, it is going to be either the Cantor space, or it is going to be a finite space. It has to be a zero-dimensional compact space, and it turns out that these are the only options. So in a way, we know where to look. Of course, that doesn't tell us anything about how the action looks like. The examples that are known to determine when they are metrizable, this is done by structural Ramsey theory. Then we always do know what the action is. But that's one technique that we have, and that's another thing that I'm trying to work out, but I'm taking a break from it, is to find out some group topological criteria for when this is metrizable. So here we are going to be looking at the opposite spectrum when they are not metrizable. And as I said, for integers, the universal minimum flow is known. The phase space, so not the action, is this modification of the Cantor cube of weight continuum. But what is interesting is that this is not the case only for integers. This is actually the case for arbitrary countable discrete group. So again, we have now a different characterization for the metrizability. This is really equivalent to some Ramsey phenomenon appearing here, we have something in terms of topology and size of the group. So now the idea is, can we somehow keep extending this picture and have more classes of groups that all share the same phase space as the universal minimal flow, and then of course try to figure out how the actions work as well. Okay, so what I will be focusing on in this talk are locally compact groups. And when we cannot solve something in general, then we look at more restricted classes. So I will be looking at non-Archimedean groups mostly, which are exactly the groups of automorphisms of structures not necessarily countable. That's not important. And then this still is not resolved completely. So I will be looking at these groups that admit invariant neighborhoods under conjugation. And then for the algebraic operations, well, the simplest one would be products or semi-direct products, but then it also depends on what they are products of. So if one of the summands or factors is compact, then we know that works well with respect to products, but you can then extend that to short exact sequences where we are extending by a compact groups. But then when we go to products beyond with compact, then the situation gets different. Okay, so let's look at locally compact groups. So these are groups that are topological groups, but they also have the topology locally compact. That means that they have a basis of compact neighborhoods. And we just showed that locally compact groups act freely on universal minimal flows. What it means really is that if you look at any point and its orbit, then that orbit is going to look exactly like a copy of G. So you can think that every orbit is a Cayley graph of G with respect to G being the generating set. Which is something that doesn't happen in those cases when M of G is metrizable, for instance. And as a consequence, actually, Kechris-Pestov-Todorovic showed that if because of the action being free, but also the compactness of neighborhoods played a role in there, the universal minimal flow is going to be non-metrizable. If G is metrizable itself, then it will, however, be approximable by metrizable ones as an inverse limit. And this is the theorem that I mentioned, and it took a while to get to the final statement that for every countably infinite discrete group, the phase space of the universal minimal flow is this one space, which is extremely disconnected sort of cover of this Cantor cube of weight continuum. And this is really all that I am aware of as explicit computations of universal minimal flows that are non-metrizable. So I started trying to look at different examples of locally compact groups, and I found a theorem of Kechris and Sokic, where they restricted themselves to Polish groups and a semi-direct product with a compact metrizable group, which turns out not to be important in there. But here the universal minimal flow behaves nicely. That is that together, even with the action, you get the product of the universal minimal flow with the compact one. We said that the universal minimal flow of compact is itself, right? Okay. So now we can do a little bit more general result where it's not just a product, but more general notion of an extension, which Christian was also talking about extensions. And that is extending a group K, group H by some group K. So K can be thought of as a closed normal subgroup, and H is then the quotient. And one can show, and this is a baby theorem, but we will hopefully extend it, that if K is compact and open, then the phase space of M of G is compact times the universal minimum flow of the quotient. So if K is open, that is what we have here, right? Then we get that G mod K is going to be discrete, right? So and what K does for us, what does compactness do for us, is that if I take an orbit with respect to K, then this is already a subflow because it's closed, so it is compact. So we can sort of split M of G into copies of K and then find out a selector through these copies that will be homeomorphic to M of G mod K. So for motivation, why these groups are interesting, or how do they somewhat natural appear, is that if I take an arbitrary locally compact group and I take its the connected component at the neutral element, this is a closed normal subgroup. So I get a short exact sequence where the quotient, excuse me, by the connected component is totally disconnected. So this is a totally disconnected locally compact group, TDLC for short. And these are examples of what we are looking at. So in a way, you can think of it that you're decomposing this locally compact group into this TDLC group that we can apply our theorem to, and a connected component where there's a lot of structure theory for connected locally compact groups. And by Van Danzig's theorem, TDLC groups are actually zero-dimensional. They admit a basis at the neutral element of open subgroups. So for concreteness, if we just restrict ourselves to Polish groups, it turns out that the underlying space has to be either finite or a countable discrete set or a Cantor space or a combination of these. So the one that is new from this theorem is when I have one that is not compact, non-discrete, therefore it has to be, the underlying set is homeomorphic to the product of infinite with Cantor, and then we get that the phase space of the universal minimum flow is now the huge space, the underlying the phase space of M of Z times the Cantor space. So now the question is, does this go beyond in these TDLC groups? Sorry, no, in TDLC this is resolved. Sorry, there's another question I want to ask. Okay. So now where we would like to move from here to would be to a little more general setting. And it turns out that, we might not have normal compact open normal subgroups, but maybe we have compact conjugation invariant neighborhoods. And we only needed one, right? We didn't need a whole neighborhood of open subgroups. We actually just needed one normal open subgroup. So these are what I'll call in groups, which are just a very slight generalization of little more known notion of Syn groups, which is for small invariant neighborhoods, where you have a whole basis of compact conjugation invariant neighborhoods. And there we have that each of these are represented by short exact sequences. So Syn groups are extensions of discrete groups, arbitrary size, by a product of a vector group with a compact group. And then the in groups are extensions of Syn groups with compact groups. So now the idea is to try to modify the argument to cover more general class of groups that are not necessarily having basis of subgroups. And when we are looking at the Syn groups, right, we have this factor in here, which is R to some power of n. And the phase space of M of R was determined by Turek, and he showed that this is homeomorphic to basically the product of integers, the universal minimum flow for integers with 0, 1. So you can think of real numbers as integers times 0, 1 modulo gluing these consecutive intervals. So that's where this E comes from, where you just extend it. And this works very well. It's actually, if we knew what M of Z was, then this would really come together with the action. And my undergraduate student has extended that to all finite powers of R, which was a straightforward argument, but stepping up dimension can bring some difficulties. So this is what's on the table right now. And of course, then even for the ones that have neighborhoods of identity of open subgroups, then we still had the normality in there. So there are many that do not satisfy that, and that's another direction. Okay, so let's now make some sort of a transition and focus on motivation for looking at products. Now we're, of course, you can think of that as a short exact sequence as well, but we don't have compactness present anymore. So extensions of discrete by discrete, we do not know anything about, really. So one motivation to study that is to look at groups that have two-sided invariant metrics, which is a particular case of Syn groups. And why am I looking at them is because there is a nice structure theorem for the non-Archimedean ones, which is those that admit a basis of open subgroups, not necessarily normal, but that will be the case if we put both of these together. And for Polish non-Archimedean groups, admitting the two-sided invariant metric is the same thing as being a closed subgroup of a countable product of countable discrete groups. And it is the same thing as being an inverse limit of a countable discrete group. So this is not difficult to show, but it gives us an idea that maybe we should understand products if we want to build these universal minimal flows from simpler pieces. And now we are going potentially beyond locally compact groups, right? Because not all of these have to be locally compact. So this is sort of looking at these TSI groups in two different ways when they are locally compact. And the inverse limit item here works very well when we go into universal minimal flows, but it's very abstract. So we know that it's if I have an inverse limit of groups, then the universal minimal flow is going to be also an inverse limit, but we do not really understand how the connecting maps look like. We don't even know what happens when we are just looking at a product of two groups. So this is what I have been looking at with Ola Kwiatkowska. And this is looking at just integers cross integers, which the first thing would be that maybe the universal minimal flow of z squared would be just product of mz with mz, which turns out not to be the case, because we had that for arbitrary countable discrete group, actually for arbitrary discrete group in general, the universal minimal flow has to be extremely disconnected. The Boolean algebra of Clopens has to be a complete Boolean algebra. But if I take a product of two extremely disconnected spaces, it is not going to be extremely disconnected. So this is not very enlightening as for what the difference is in between them, but we know that they are not the same thing. And this is in contrast to the other side of the spectrum, where the universal minimal flows are metrizable, where Gianluca Basso and Andy Zucker show that the universal minimal flows are productive. And funnily enough, the argument is somewhat related to the one for the extensions by compact groups. So we started looking into the product of integers, and I wish I had a complete answer and told you exactly how we can get z squared out of z. But it seems to have a lot of interesting questions, and that it has been studied in set theory a little bit when we look at the space of all ultrafilters in which M of Z lives. So we are coming back to the Chipstone compactification, because the universal minimal flow lives inside as a minimal subflow. So we will describe how we can view beta Z as a flow and as a semigroup, and try to use that to understand the universal minimal flow. So this is a general statement where Z can be replaced by any discrete group. So it's interchangeable for integers and integer squares. So I will be saying things just for integers. And if there are any questions, please ask anytime. So beta Z is the space of all ultrafilters, where the topology is given by a Clopen basis, where we take an arbitrary subset of integers and we look at all ultrafilters that contain the set. So you can also think of it that the Boolean algebra of Clopen sets is exactly the power set of integers, and then beta Z is the stone space of that. And now, of course, there is a simple relationship between Z cross Z and Z, which are the two projections, right? So I have Z cross Z, and I have a pi1 projection on the first coordinate and pi2 projection on the second coordinate. And then each of these maps, because this is a continuous map, of course, as both of these sets are discrete, this does extend into some pi I bar from beta Z cross Z to beta Z cross beta. Sorry, it's just to beta Z. And then if I look at this pi, this is just the two coordinates of the pi1, pi2. So, you know, if things were simple, then this would just be a homeomorphism, but it turns out not to be. And there has been some investigations, although not very many. And there are some surprises in looking at the sizes of preimages. So I take arbitrary PQ in beta Z, and I look at how many elements of beta Z cross Z are mapped onto that. And if either one of the P or Q are in some minimal subflow, which we said that this is the same as the universal minimal flow, then the number of preimages is going to be infinite, and from some topological considerations, it's going to be 2 to continuum. This is also the case if, and this is where we will be looking at the semigroup structure of beta, where we have an idempotent. And it's also the case when, and we get something very different when we look at special types of ultrafilters that do not have to exist. So when we do have selective ultrafilters, then we can have finitely many preimages, 2 or 3. We can never get 1, but we can get 2, we can get 3. And selective is a special case of being a p-point. So, and actually this is the only restriction for not getting infinitely many preimages, and that is if we have no p-points and if they're related to p or q, then we get infinitely many. So I'm not going to be really talking about those. We have been trying to use that, and we have not really gotten further than getting 2 preimages in what we want. So I will not really be talking about it, but just as a reminder of the definitions. And these proofs are very combinatorial in nature. They do not actually use, I would say, at all the dynamical structure and little of the semigroup structure. So we will try to use that a little bit more. So as I said, we can see beta Z as a flow, and we said it at the beginning that we can act by translating every set in the ultrafilter by that fixed number. And then M of Z is going to be isomorphic to any minimal subflow. So in particular, all of them are isomorphic as flows, which is a general phenomenon as well. And then what we are interested in is that when we look at this pi map, where do preimages of what I call minimal elements, so elements that come from some minimal subflow, live? So when we are now trying to investigate M of Z cross Z with respect to M of Z squared, what is the relationship? So we will also be using that we get a semigroup structure. So this has been used a lot in additive combinatorics. And there is a beautiful book by Heinlein and Strauss that introduces this in generality. So we have this action, which actually gives us addition that is going to be only one-sided continuous, that is that if we fix the second coordinate, then we will get a continuous function, and we get a compact right topological semigroup, which has a lot of structural properties. And then the minimal subflows become also minimal left ideals. So they become, they now are, have algebraic meaning inside. And those minimal ideals stack up, minimal left ideals stack up into a minimal both-sided ideal. So how I sort of think about it is that I have integers here, then I have the huge wild beta z in here, and then I have some of this semigroup structure inside that goes well with with flows as well, and that is that I have these minimal left ideals, which have to be disjoint, of course, and we know that there is a lot of them. And if I take the union of all of them, then I get the minimal both-sided ideal. This is not a subflow, the minimal both-sided ideal, because it is not compact, it is not closed. There are elements that are in the closure that are not in any minimal left ideal. And now we will be restricting our attention to there, because we are interested in the minimal left ideals, the copies of universal minimal flow inside, how they interact. So if I look at this map, there is a result by Moche where she was trying to actually prove that maybe when I restrict to this nice minimal both-sided ideal, then the map could be better behaved. Maybe it could be finite to one, maybe there could be a nice way to describe it, but it turned out not to be the case. And our result is finding where these preimages come from. And when I take any pair coming from two or single minimal left ideal, then the preimage is going to intersect infinitely many minimal left ideals in beta z squared. So they sort of, as I was drawing this k, k of beta z squared, right, as the union of minimal left ideals. Now we know that if I look at preimage of two elements that come from m of z, then they are going to appear in infinitely many. We cannot have that argument that it is 2 to c many, because it is not closed. So that is not clear how many of these ideals we intersect, but infinitely many. So this is one direction that we were looking at, sort of this in the picture vertical. Now let's look at more horizontal, and that is looking at a single one, right? Maybe what if it was the case that if I look at one minimal left ideal here on the z squared star, that there would be just one element that maps onto a given pair. So that also turns out not to be the case. So we said that first of all, these cannot be the same. But now we can use the semigroup structure, because the pi, the projection, preserves the operation as well, even when extended to beta. So this is a continuous semigroup homomorphism. And then because M is can be viewed as an ideal, this is also a semigroup. So I get the semigroup structure for the map here as well. And now every compact one-sided continuous semigroup has an idempotent inside. So these are nicely behaved, and when I have a semigroup homomorphism, then the preimage of idempotence has to be a subsemigroup, and that gives us all the power in here that we have so far used. And that is that we think that we know that preimage of a pair of idempotents contains a non-idempotent, but this has to be still written up. So that's why it's a conjecture theorem. But if it's the case, then we know that the preimages have to be infinite, and therefore there would be 2 to c many preimages in a single minimal left ideal. So why would that be the case? And this goes into even more structure, which is something that I'm very fascinated about for years now, that if I look at one of these minimal left ideals, so identified as the universal minimal flow, this splits as a semigroup into a maximal subgroup, so largest subgroups that are in there, where each of them has an idempotent as an identity. And in particular, these subgroups actually are isomorphic to group of automorphisms of M of Z squared. And Zelenyuk showed that and now you can replace that squared with arbitrary discountable discrete group with no torsion, you will find no non-trivial finite subgroups. So the only subgroups that you will find in there are idempotents. And if you have a subgroup, you might not have inverses, right? So not every element gives you a subgroup, but if they do, then they have to be infinite. Well, but then because M of Z cross Z has all of these subgroups inside, then if I have some element that is a non-idempotent that maps onto a pair of idempotents, then I will get that there is a whole subgroup, because I know it's a subsemigroup that maps onto EF that has to be infinite, right? So I get this subgroup, just the cyclic subgroup that maps onto there. So that looks like this is going to be the case, and then of course it's there's a lot of questions, but these are very as I said, there is no final result of what the relationship already is. And there is the last thing that we are trying to investigate, and I think this is something that's somewhat surprising, and hopefully we might get some sort of similar result as Andy with Gianluca got, or when we were looking at these short exact sequences, by using orbits and orbit closures. So when I look at one of these projections, right, and for every element, the pre-image is a Z flow in the other direction, right? So if I have a projection on the X coordinate, then every element is going to give me a Z flow in the other direction. And it turns out that this, why did I put it in here? I'm sorry. So this is going to be relevant afterward, that these flows actually, they break into minimal subflows, right? So I can look at, I have projection from M of Z squared onto M of Z. And then for every element, I get a pre-image, which is a Z subflow when I'm looking at this direction. So I can take an arbitrary point in here, and I can take an orbit with respect to this direction and its closure, right? And I didn't see a priori why this would have to be a minimal subflow, right? It could be something else. It could be a copy of beta Z, but it turns out that it is a minimal subflow, and I would like to see some very direct proof of that would not go over it's not a detour, but it seems like something that should be either obvious or not true. So we can actually split M of Z squared into these copies of M of Z, which sort of gives you like the idea it should be the product of M of Z with itself, which is not. And then the advantage of that, as in the case of the compact group, is that you can look at the quotient space. You can look at M of Z squared together with these copies of orbit closures with respect to the one dimension, right? Because they are all disjoint. And now the question is, what is this? It is not M of Z. So how does this look like? So this is the current state of affairs. And let me just tell you how we go around this. And this is really how I view universal minimal flow, sort of more in the dual notion of the Klopen algebra of Klopen sets. And these sets are in the minimal flows synthetic. And that is in integers, it means that I have bounded gaps. In general, it means that finitely many translates cover the group. And where do they come from? Well, they come from these return sets. That if I have any minimal flow, this is the same as for every element and every open neighborhood of that element. If I look at all of those here in general G's that bring that element close to itself, then this is a large set. This is a synthetic set. It has bounded gaps. And now when we go through these, well, they have nice properties with respect to translations and intersections. And then it turns out that if I look at these return sets for the product of integers with themselves, then they are not arbitrary synthetic sets. Well, there's many things that they have to satisfy, but in particular, when I look at either lines or the columns, then these are all synthetic or empty, right? I mean, of course, I could have a set that would be all integers except, or square of integers except for one point, and that would still be synthetic, but it wouldn't be one of these return sets, and this is what gives us that. In the end, these orbit closures are minimal, so I can break it into copies of M of Z. So as I said, this is very much a work in progress, and if you have any suggestions or maybe something in literature that we have missed, I would be very grateful for any indications, and thank you for being here.
Thanks, Dana. Any questions for Dana? So, sorry, I'm like very dark. It got dark without me noticing.
I can imagine.
Yeah. Well, you gave a great talk, so I didn't, have time to go turn on the lights. Wait. I have a question. I mean, my question is in general. So you guys don't have any conjecture as to how it looks like based on your findings about the pre-images?
Yeah, there is some. It's very puzzling. We sort of are starting to understand how the pre-images are related to themselves, and it's sort of getting formed. But no, it's what is the thing that's missing when you take the product M of Z with itself? It's still somewhat mysterious. There is a step. There is a when you look at the product of M of Z with itself, we said this is not extremely disconnected, so you could take that Gleason cover, so you would get an extremely disconnected space, and you could think maybe this is it. That would be the most natural thing. But then Andy Zucker gave me an example of a set, one of these return sets that breaks that conjecture. That means that there is still something more missing, and that's something that so there is sort of it's a two-step process. I think this is also somewhat interesting, right? We have that M of Z cross Z is not extremely disconnected, so you can think of that as embedded into this Gleason cover, which would be extremely disconnected, but then it turns out that it is still smaller than M of Z cross Z. And so what we tried to first do was actually to more understand what comes more into this guy, and we got something, but it's still not clear what that is. And then when we sort of left trying to understand that and just looked at the relationship of these two, we got further, but still it looks like there should be some sort of closure operation. You would like to think that you still build it from M of Z with M of Z, and then you do some operation to it. But...
Okay. Yeah, very interesting. Any other questions or comments for Dana?
I have the question, Dana.
Good to see you all.
Do you have do you know of any classes of groups where beyond locally compact where you have non-metrizable minimal flow? I mean, there's some natural classes.
Right. Yeah. That's also like there's two things: either that they are not metrizable, and also that's related to having a free action on the universal minimal flow. So the TSI groups, they don't have to be locally compact, but they will satisfy that. So whenever you have a continuous homomorphism onto a discrete group, for instance, then so abelian non-Archimedean groups. So, but that's cheating, right? Nothing that would be somewhat more substantial.
I mean, so these groups with bounded geometry, they have that property. If you're unbounded but still have bounded, okay, it's confusing notions, but if you have bounded geometry but don't have property OB, then you have this. Then you have some amount of freeness on in the action on the universal minimal flow. So, but
okay,
you have to see some big class of groups with this property.
Right. Yeah, that I would be happy about. I know that I should look more into that as well. I was thinking that the CLI groups might work.
The left invariant matrix. Yeah.
Right. But that's still not clear.
But then
Do you
that
have
would
any
include
idea?
every Syn group.
Right. So that would be a larger. Well, in the non-Archimedean, yeah, you cannot, yeah, just in the non-Archimedean case in this, for now, not in general. CLI groups will not work in general, of course. But.
Okay. Any other questions to Dana? Or if not, let's thank Dana again.